Welcome to this Vaisala webinar on wind research in complex terrain with contributions from colleagues from the Karlsruhe Institute of Technology, or short KIT. I am Jana Preisler and I'm working in the science department of Lidars, which is a Vaisala company. Complex terrain brings its own challenges for weather and air quality forecast, mostly due to unexpected and complex airflow patterns in such locations. And today, our colleagues from KIT will talk to us about how they are using pulse Doppler lidar instruments to map wind fields in such complex terrain. For their research, they are using three Vaisala WindCube scan Doppler lidars simultaneously. We will hear about some of their campaigns from current and former KIT researchers Bianca Adler, Nevio Babic, and Philip Gash. After their presentations, we will conclude this webinar with a panel discussion as well. And it is my pleasure first to invite Bianca, who will introduce KIT and speak about the UC² campaign in the Stuttgart Basin in southwest of Germany. Bianca, the floor is yours.
My name is Bianca Adler, and on behalf of my former colleagues at KIT, I'm now giving a brief introduction into the KitCube, which is the advanced mobile observation platform at KIT. So KIT stands for the Karlsruhe Institute of Technology, and it was founded as a merger of Karlsruhe Research Center and the University of Karlsruhe in 2009. It's located in southwestern Germany and has nearly 10,000 employees, with more than half of them in research and teaching. Meteorology in Karlsruhe goes way back. The first measurements were taken in the 18th century, and the Institute for Meteorology was founded in 1929. The Institute of Meteorology at KIT is split into 4 departments, which cover a large range of research topics throughout the whole atmosphere. The KitCube is deployed by IMK-TRO, which stands for Troposphere Research, and which does fundamental research on climate, water cycle, and trace gases. So what is the KitCube? A KitCube is a mobile integrated atmospheric observation system which allows for a most complete probing of the atmosphere within a volume of around 10 times 10 times 10 cubic kilometers. It combines different in situ and remote sensing instruments which allow us to cover complete process chains. It also incorporates the intelligent instrument control, which allows for a maximum synergy of complementary measurements techniques and also to combine different instruments. So Doppler lidars comprise a major part of the KitCube. At IMK-TRO, there's long-term experience in the deployment of Doppler lidars since 2004, and currently there are many Doppler lidars within the KitCube. There are 5 scanning WLS200S and 1 profiling WLS8, both from Lidars. Then we deployed 2 Lockheed Martin wind tracer systems and 1 airborne scanning Doppler lidar system. So in the following, I will now show you an example on how we use these Doppler lidar measurements to resolve flow features in a complex urban environment. So the target area for this study was Stuttgart, which is a major city in southwestern Germany. It's located in mountainous terrain and it's well known for its bad air quality. And this bad air quality is related to the fact that the downtown area of Stuttgart is located here in this valley-shaped basin called Stuttgart Basin, which opens into the larger Neckar Valley in the northeast. Due to the terrain surrounding the city, there are different thermally driven circulations which develop. These include valley winds, in and out flows from the basin into the valley, and slope winds. So to improve the air quality forecast for the city and to facilitate urban planning, it is important to get a better understanding of the flow features in the complex terrain around Stuttgart. therefore, we conducted measurements of the horizontal flow field over the urban area within the UC Square program in 2017-2018. So this is the Doppler lidar measurement setup. So we deployed 3 WLS 200S and installed them at slopes, like opposing slopes overlooking the Neckar Valley here and the outflow region from the Stuttgart Basin. The lidars were installed at roughly at the same height, and they performed horizontal PPI scans at around 70 meters above the valley topography. And the repetition rate of these scans was around 1 minute. So each of the colored sectors here gives the scan sectors of the individual lidars. So in the overlap area here, we could then retrieve the horizontal wind field. In addition to these horizontal wind measurements in one height, we also deployed a profiling lidar, the WLS-8, here in the Stuttgart Basin, and it provided us with horizontal wind profiles. So this is now a 24-hour video showing the horizontal wind field in the overlap area of the lidar measurements, and it starts in the evening. So you can see here an outflow from the Stuttgart Basin into the Neckar Valley, and then you see here in the Neckar Valley like down valley wind developing in the course of the night. It becomes stronger in the morning hours. We have a lot of variability here over the slopes in the southwestern part. Then in the morning, down valley wind weakens. We come into the transition to the daytime boundary layer, and then we have convective cells developing, and they are visualized by these areas of high and low horizontal wind speeds. And we can see that these convective cells move through the investigation area from east to west, which means that they were like advected or transported with the mean horizontal wind. So this highlights again just some of the observed structures. So during nighttime, we saw this outflow from the Stuttgart Basin into the Neckar Valley. Then we saw this down valley wind in the Neckar Valley, and we saw a lot of variability near the slopes, such as this vortex here forming in the middle of the night. During daytime, we saw like convective cells, which were linked to these areas with like low and high horizontal wind speeds. And the high spatial and temporal resolution of the retrieved wind fields allowed us to track these convective cells. Like here in this example, the cell moves from east to west. So the measurements now allowed us to track these convective cells and to estimate the convection velocity, which is the speed with which the cells move. So for this we used a simple method. We determined the mean wind direction for a 1 hour period, and then extracted the horizontal wind speed along the line of this mean wind direction through a point in the Neckar Valley. And this is what you see here in this plot in the middle. So the y-axis shows the time for 1 hour, and the x-axis shows the distance from this point in the Neckar Valley. The color gives the horizontal wind speeds extracted along this line of mean wind direction. So these areas with high and low horizontal wind speed represent these convective cells, and the slopes of these elongated streaks give us the convection velocity. We then used a two-dimensional autocorrelation function for each of these 60-minute periods to determine the slope of these streaks. And then we compared this so determined convection velocity with the horizontal wind speed measured at the height of the lidar scanning plane and 100 meters above. And we actually found that the convection velocity was more similar to the wind speed measured higher up. So this means that the cell which we saw moving through the investigation area were actually steered by the flow higher up and not by the flow at the same level. So this was just a brief glimpse into the measurements we did at Stuttgart. If you're interested, you can have a look at our paper, which just got published earlier this year.
Thank you, Bianca. Next, Nevio will tell us about the LiDAR measurement campaign studying cross-valley winds in the Inn Valley as part of the Cross-In experiment.
My name is Nevio Babic. I am a postdoctoral researcher from the Karlsruhe Institute of Technology. Today I will talk about the Cross-In campaign. This is a campaign we conducted in the Inn Valley in Austria during the summer and autumn of 2019. It stands for Cross-Valley Flow in the Inn Valley investigated by 12 Doppler lidar measurements. Essentially, we wanted to explore and investigate more about these cross-valley flows, which are, even to this date, not well represented in numerical weather prediction models, and we still have lacking observations. Our study site was located about 20 kilometers to the east of the city of Innsbruck. We focused our measurements at 3 locations: Kolsas at the valley floor, Marbach on the northern slope, and Hochhäuser on the southern slope. The black line indicates the scanning plane of the wind cube, so something I will talk about in a few more slides. Because we have lidars on the slopes, especially in complex terrain, it becomes quite challenging to deploy them or even to access the slopes and then to deploy them. And it requires some quite unconventional means, as well as the voluntarity of local farmers, for instance. Bringing power to the instrument is also quite challenging over such a steep terrain. This is the case over the northern slope at Marbach, where also the terrain is also quite inaccessible and required some unconventional type of transport to deliver the lidar to the site. The 3 lidars performed overlapping range height indicator scans. Each scan lasted 1 minute. They were all synchronized with their start and stop times by utilizing the API feature. This is the perspective from the Hochhäuser on the southern slope. This is a sample of a typical radial velocity field on this particular day, where we see that we had quite intense horizontal airflow above 1,000 meters and a bit weaker airflow below. The perspective from the valley floor site, which agrees in terms of the distribution of strong winds above 1,000 meters and weaker winds below 1,000 meters. And finally, the perspective from the northern slope, and incidentally, the scan at this particular time. However, the radial velocity in its own doesn't really give us the information about the actual wind vectors. However, if we look at all 3 scans simultaneously, we can see that their scanning regions were highly overlapped in both space and time, and this enabled us to actually perform the so-called dual Doppler retrieval algorithm by retrieving the wind field or the 2-dimensional wind vector in this scanning plane on a Cartesian mesh of 50-meter resolution. The method relies on going grid point by grid point, collecting all radial velocity measurements inside a circle of influence, and then solving a linearized system of equations by minimizing its cost function. This enables us to get the actual wind vector in the scanning plane that is composed of the 2 wind components, the cross-valley wind speed component and the vertical wind speed component. So to give a couple of examples, on the left we see that cross-valley wind speed component V, in the middle the vertical wind speed component, and on the right it's their combined effect. The dotted line indicates the average ridgeline level. In this case, we see that we had very strong winds above the ridgeline, which were primarily of southerly fetch, but also we had very strong mountain wave events, as well as a small rotor behind the mountain wave event. Another example of a rotor that was located a bit more deeper in the valley and over the valley floor. An example of a rotor so-called train, in which we see alternating pattern of ever diminishing rotors, as evidenced by these patterns of updrafts and downdrafts in the middle. Precipitation was also quite easily sampled, as evidenced here by very strong negative vertical velocities depicting the falling hydrometeors. We also sampled and were able to sample quite more quiescent conditions, in this case mountain waves along the ridgeline, which were quite weaker than the previous examples. Isolated convection was also observable, in this case this convective thermal above the northern slope. Subsidence, which is a broad region of negative vertical velocity, was also sampled quite easily. One of the more common features we saw was this pattern of strong updrafts over the southern sidewall and strong subsiding motion over the northern sidewall, which results in a sort of a clockwise circulation from this perspective. This is not an artifact because we can compare this with aircraft in situ measurements that were collected at the time when this scan on the left was taken. The aircraft flew 5 cross-value legs at this time and also observed the same clockwise circulation. Overall, Crossan provided a comprehensive 3D perspective on the thermodynamic state of the mountain boundary layer in the in-valley, and specifically the 3 wind cube systems proved very invaluable in sampling this cross-valley flow structure. Thank you for your attention.
Very interesting presentation, Nevio. We will now hear from Philip about the Doppler wind lidar on board of an aircraft, also measuring in complex terrain.
Hello and welcome to my presentation on airborne Doppler lidar for boundary layer research in complex terrain. My name is Philip Gasch. I work at the Karlsruhe Institute of Technology, KIT. To begin with, I would like to ask you to imagine for a second what it would be like if you could see the wind blow across an entire mountain range. Surely, valuable insight into boundary layer structure and characteristics could be obtained if we were able to do so. In this talk, I would like to show you that airborne Doppler lidar is a technique which allows us to do exactly this. Now, why are we interested in airborne Doppler lidar? In the previous talks, Nevio and Bianca have already demonstrated the great potential of combining multiple ground-based systems for remote sensing of the wind field in complex terrain. However, even combining multiple of these ground-based systems can only cover fixed and limited spatial domains. Further, Nevio's talk also illustrated some of the challenges associated with deploying multiple of these instruments in complex terrain. Despite the challenges, more widespread and more flexible measurements of the wind field in complex terrain are desirable. Airborne Doppler lidar can offer a way forward in this direction. It allows for spatially resolved as well as targeted measurements. Below, you see an example of such a measurement obtained with an airborne Doppler lidar across the Harz mountain range in Germany. So the total transect length here is approximately 40 kilometers. You can easily imagine that such a long distance could not be covered by currently existing Doppler lidars, and even combining multiple of these Doppler lidars cannot cover these extended spatial transects, which are nevertheless very interesting to look at. In the following, I will fill you in with how these measurements are obtained and also some details and what you can really see in them. What does an airborne Doppler lidar actually look like? I'm showing you a very simple example of a prototype system that we've constructed here at the KIT together with the University of Braunschweig in Germany. The system simply consists of an aircraft and a lidar. You see the aircraft on the left-hand picture. That's a Dornier 128 operated by the University of Braunschweig for more than 20 years already. This aircraft is also equipped with a 100 Hz turbulence probing equipment that's also very useful for measurements inside the boundary layer. Inside this aircraft now we've installed the lidar that you see on the right side picture. That's a WTX 1.6 micrometer wind tracer system which has been used by us for ground-based measurements for more than 10 years already. This lidar, as you see, is now fixed to the aircraft floor and staring nadir outside of the aircraft through an opening in the floor. Because it's staring nadir, if the aircraft is flying straight, then the default measurement is the vertical wind measurement. However, scanning for wind profiling can still be conducted through banking the aircraft in turns. That means if the aircraft is not flying straight, the lidar is not pointing nadir, and then a portion of the horizontal wind is projected into the measurement and can be used to retrieve the horizontal wind, also similar to a ground-based VAD procedure. In the following, I would like to show you some results obtained from flights in the vicinity of Braunschweig in Germany in July 2019. Of course, airborne Doppler lidar measurements require sophisticated data processing scheme because the lidar does not only measure the atmospheric contribution, instead it also measures the aircraft contribution to the radial velocity, and that needs to be corrected very reliably. Unfortunately, there's no time to go into details here. Instead, I would like to focus on the application examples in the following. Coming back to the example which I've showed you previously already, I would like to show you now an example where the airborne Doppler lidar was used to fly transects across the Harz mountain range in Germany repeatedly along the same ground path. This provides us with the measurements of the vertical wind at highest resolution up to date, thanks to the slow aircraft speed and high lidar measurement frequency. And these transects really show that the airborne Doppler lidar is able to capture both spatial and temporal variability of boundary layer development in complex terrain. Now, what you see here actually in detail is then the aircraft flying at 3,000 meters. So that's the thin line indicated at 3,000 meters there. And then below this, you see the lidar measurement curtain. So that's the default vertical wind measurement along this curtain across the Harz mountain range. And then, as I said previously, scanning can be conducted by flying a circle, and that was done at these vertical black lines there, shown there. So along these vertical black lines, you see the magenta wind barbs, which show the vertical profile of the horizontal wind obtained from these circles. So, looking at the example from the previous slide, again here in a 2D view and with a slightly adjusted color bar range, you see some interesting features of the boundary layer across the complex terrain. This is an early morning transect, the first of 3 that I will show you, conducted approximately 3 hours after sunrise. And associated with these early morning situations, there's a strong spatial structure of the boundary layer development and the turbulence associated with it. So above the peaks, you see the peak here, the highest peak is the Brocken mountain at an elevation of approximately 1,000 meters. There, some updrafts reach quite high, more than 500 meters above ground, and these updrafts are almost semi-irregularly spaced with downdrafts in between them. And then as you go from these higher elevations towards the surrounding lowlands, boundary layer height decreases, and associated with this decrease, the updrafts are weakened but also spaced closer together, because boundary layer height limits the updraft spacing and structure here. So that can be really shown by the airborne Doppler lidar measurements now, and that would be really hard to capture using ground-based systems in such a way. The same transect was repeated an hour later along the same ground path, and that's shown here now. So as would be expected, boundary layer evolution has progressed further, so it generally reaches higher everywhere, and these updrafts have increased in intensity, but are now slightly spaced further apart. The downdrafts, on the other hand, have not increased in intensity much, it appears here. Instead, they also cover a slightly wider range compared to before because of this increased boundary layer height. On top of the boundary layer, especially above the higher peak here, the Brocken mountain, you see that some clouds are starting to form on top of the boundary layer now, and there the lidar is not able to penetrate, thereby no vertical wind measurement can be obtained below these clouds in this transect here. Additionally, you also see some clouds forming not associated with the boundary layer development here, this for example, an autocumulus field at a distance of 30 kilometers from the Brocken. So of course the Doppler lidar does not only measure the wind speeds along the flight path, but it also provides a signal to noise ratio, and that's actually another interesting quantity to look at here, because it provides some further insight into the boundary layer structure. So associated with these winds you saw before, you can clearly see a difference in the signal to noise ratio above the mountains, but this new boundary layer is actually forming inside the residual layer already. So even above this boundary layer that's forming, there's elevated concentrations of backscatter visible here. Of course, in the surrounding areas, this cloud scene is also complex. So associated with this elevated autocumulus field at 30 kilometer distance, there's also some increased aerosol layers being present in that region at higher elevations, not connected to the boundary layer. So, because the Doppler lidar is not able to penetrate these clouds that you saw on the previous example, this transect was repeated directly after the one I showed you, and by retracing the flight path along the same ground track, but now with the aircraft flying below cloud base. So you see the aircraft here ascending towards the Brocken. It's flying from right to left actually. So as it enters this Harz mountain range, it's ascending because cloud base is ascending there. You see the in situ measurements of the aircraft displayed at this 400 meter distance above the above the LiDAR measurement. And as the aircraft is ascending with the ascending cloud base, then suddenly it enters also the boundary layer from the complex terrain. And then you can really see these updrafts protruding all the way from the LiDAR into the in situ measurements from the aircraft as well. So that's really where these clouds are present, and then the updrafts couple all the way from the surface into the in situ measurements and obviously into the cloud above the aircraft there. Coming to the conclusions from the application examples which I've showed you, I tried to show you that airborne Doppler LiDAR can really help us advance boundary layer research in complex terrain. It does so by allowing for spatially resolved observation of flow phenomena, thereby providing information that's really hard to obtain using ground-based measurements alone. Specifically, airborne Doppler LiDAR enables us to retrieve vertical profiles of the horizontal wind as well as vertical wind statistics. So going beyond what I've showed you here, my work also shows that it's really possible to quantify vertical wind mean as well as variance inside the boundary layer using such a system. What I've shown you was that the new system, thanks to the slow aircraft speed as well as the high LiDAR measurement frequency, provides the vertical wind at highest resolution up to date, giving detailed insight into these updraft structures and their behavior in complex terrain. So of course there's a few things upcoming here. We have a scanning system planned that's supposed to fly soon, and then more measurement campaigns in the next year associated with this new system, also in complex terrain. And of course it makes sense in complex terrain especially, but also generally, to combine these airborne Doppler LiDAR measurements with ground-based measurements, because then the airborne Doppler LiDAR can cover the spatial variability of the flow over extended transects, but also the ground-based systems can cover the temporal evolution of the flow field along these transects at fixed locations. And thereby, I think combining these two systems, really new insight into boundary layer structure above complex terrain can be obtained in ways that was previously impossible to look at them. So I think this is really exciting to combine these two systems in the future. And with this, I would like to thank you for listening. I hope you enjoyed it. And yeah, I hope to see you in the real world at some point. Bye-bye.
Thank you, Philip, for your presentation. After having a good idea of the work of KIT with their Doppler wind lidars, it is time to invite our speakers for a panel discussion where we cover a few more detailed questions on the three top projects. Thank you, Bianca, for your interesting presentation on the wind fields in the complex terrain around Stuttgart. Why did you decide to use 3 wind lidars and not just 1 or 2?
So what we wanted to achieve was to get information on the spatial distribution of the two-dimensional horizontal wind field. So first of all, from one LiDAR, you only get the radial velocity, so you don't get the two-dimensional wind field. So you would need 2 LiDARs at least to retrieve both wind components. And then, so the area we wanted to cover was quite large. Like it covered like a larger section of the Neckar Valley, and we were also interested in the flow at the opening of the Stuttgart Basin into the valley. And so we decided to take 3 LiDARs to cover a larger area. So it's basically like giving with the topographic constraints and like angles which were blocked by the topography. When we combine the 3 LiDARs, we can just cover a larger area. And yeah, that was the reason for that.
Okay. And how did you coordinate the 3 lidars? I guess this must be some challenge.
Yes, so in this campaign in Stuttgart, that was in 2018, and there we didn't have the API capability of the WindForge software, so that was not available at that time. So what we used was the scheduler built into the WindForge software, and we just programmed like every LiDAR to start a scan at the full minute, and then the scan lasted for 60 seconds, and then like next full minute, the next scan was triggered. And that actually worked quite well. Like it was really stable. We didn't have any like data losses that one of the softwares crashed or something. So it was running for, I think it was like 6 weeks without interruptions. And the like the synchronization time, like the start time of the lidars was also pretty accurate. Like in average, the like they all started within like less than 1 second apart. So for this purpose, this was sufficient. Someone might say, oh, if I want to like have a higher synchronization where it really like it matters, like millisecond matters, then this option is not suitable, I would say. But for our purpose, where we are more interested like in the mesoscale structures, it's sufficient.
Okay, and you have use the time synchronization using the GPS or server?
Let me think. So if I remember, I mean, it's 2 years ago. So if I remember correctly, we had them all synced to the same web server.
Mhm.
So we didn't use the GPS time. I think we used the web server time. But I'm
Okay,
not 100% sure on that.
that's okay. Could you tell us a bit more about the configuration of the lidars? So which scans you used and so on.
Yeah, so as I said, our purpose was to retrieve the two-dimensional horizontal wind field. So what we did is we set up our 3 lidars on the slopes overlooking like the Neckar Valley and the Stuttgart Basin. And we tried to find locations which were roughly or ideally at the same height above the valley floor, or well, at the same height above sea level. So, but because we had this, it's difficult in like a build-up terrain, complex terrain, to find like these locations which really fulfill these conditions 100%. So that we had like small differences of a few tens of meters where the lidars were actually at like different heights above sea level. But we took that in, yeah, that's just something we had to deal with. And then what the lidars did, they performed like PPI scans at 0-degree elevation angle, so really horizontal scans. And so we did that so that we didn't have any contributions from the vertical velocity, so that we really only measured like the horizontal wind components. And then, so as I said, each lidar started at the full minute, and then it did like one sector PPI scan lasting 60 seconds. And then, so the accumulation time was 1 second. So during this 1 minute, each lidar covered a sector of 60 degrees.
Cool. And about the results you found, can you tell us a bit more about the conditions and how they can be linked to air quality in the Stuttgart Basin and the Neckar Valley?
Yeah, so I mean, there's a lot of industry in the Neckar Valley and the Stuttgart Basin area, and especially the Stuttgart Basin often suffers from very bad air quality during winter time mainly. And this is because there's a limited ventilation of the basin, like there's not enough exchange of the air inside the basin with the surrounding air. And so this flow patterns we found, like an outflow or inflow into the basin, they can be very relevant for the ventilation of this of the basin. So so these measurements were done within a project called UC Square, which stands for Urban Climate Under Change. And within this project, like a high resolution urban model is developed, which is really able to dissolve like the whole city on a scale like down to single street canopies and houses. And our measurements will be used like to evaluate this model. So it's like with measurements, you always have these gaps. Like you can never capture really this three-dimensional flow field. You don't have temperature in our case. But then like by combining these measurements with the model, like we can get the best idea of really what's happening in this urban area.
Okay, good. Thank you, Bianca. Then maybe we move on to questions. Philip, do you have a question?
I would have a question for Bianca also, because I haven't worked with these dual Doppler lidar retrievers. Is there some standardization happening? So are there any software packages available now that you can use to do these retrievals in a standardized way, or is there any project planned like this? Do you know?
So what we use, so we work together with the group from the University of Innsbruck on that, and we used like a retrieval package which Maren Heid wrote. But it's basically based on a few equations which were already published like in the beginning of the 20th century. So it's not like we reinvented the wheel, but now like there is this software package written in Python which does this wind field retrieval calculations. And this is publicly available on GitHub.
I think Maren, that's what I heard, that she published it or that she makes it available. I think it makes sense to keep this going, because otherwise everybody has to reinvent the wheel.
Yeah, I mean, I'm pretty sure that there are other packages available. Like I know that there are other groups in Europe working on this multi-Doppler retrievals, but I don't know if they are published. So I think like what Maren did, like this is a nice starting point for future studies, especially because it's very flexible. Like you can incorporate several lidars. It's not restricted to 2 lidars. You basically can take as many lidars as you want and just like then estimate the wind component at an individual grid point, taking all lidars into account. So yeah, I think it's great.
And one more question with these dual Doppler retrievals. Did you look at turbulence also, not just at the mean flow, but also at turbulent deviation?
Yes. So with the setup we had, like we retrieved the wind field on a 100-meter grid. So this is 2 cores for like small scale turbulence. But what we saw, the convective cells, like larger convective cells were nicely visible in this in the retrieved wind fields, and we could track like individual cells, like when they propagated through the area. But like to really estimate like variances at individual grid points, I think the measurements were not fine enough or highly like resolved high enough, neither in time nor in space. But yeah, you would need a different setup. I think if you aim for turbulence, you would want to have like shorter scan times and a higher spatial resolution.
But do you think it would be possible using ground-based measurements as well in such a setup, a dual Doppler setup?
I mean, it's a little bit what Katja did, like in HDCP square. I mean, she was scanning much faster with the big wind tracer lidars, and she had a much smaller sector. And I think she saw more fine-scale turbulence structure in her scans. Yeah. So I think yes. I mean, in theory, I think it would be possible. I don't know. Like, I'm sure there is a lower limit of what you can resolve. But I think you should be able to resolve like some of the smaller scale turbulence. Something to try, I guess.
Okay, sounds interesting. Nevio, maybe we continue with you. You have told us about the Cross-In Valley campaign, which is a bit similar to Bianca's work as well. What would you say was the main purpose of this campaign?
Right, so it was also a campaign done in complex terrain. It was done in a valley that's a little bit deeper than the Stuttgart Valley, so we had to take into account the more complex terrain as well when deploying the lidars. Essentially, the goal of the campaign was to see and observe and sample the cross-valley structure at this one cross-valley transect, and then see how it relates to the thermodynamic state of the mountain boundary layer using other measurement platforms other than Doppler lidars. So therefore, the focus of the campaign was purely, it was purely observational. We didn't have any preliminary simulations performed, or simulations were in general not the goal, but these measurements can again be used for validating and evaluating model output later on.
Okay, and is there a link also to air quality in the valley? Is that an issue as well there?
So it's a more pronounced issue in the winter, because in the winter there's a lot more trapping and layering of these pollutants inside the valley. That was not our goal, because in the summer, usually the turbulent mixing is vigorous enough that there is no trapping of the pollutants in a more long-term sense. So we didn't really have a large focus on the pollution aspect. But close to our investigation area, there was another campaign in 2006 that was performed during the winter. It was a shorter campaign, but they actually observed that there is a lot of layering happening of these pollutants, which may have a detrimental impact on health, visibility, and so on, because there is a very pronounced traffic corridor running right through the in-valley, which I think has been increasingly growing in the capacity of the vehicles that use it.
Mm. And in your presentation, you show nicely that combination of multiple Doppler lidars enable the characterization of the cross valley wind. Did you also investigate wind associated with a long valley wind, or is it even possible with the setup you used?
So with our setup of 3 lidars that were aligned in a way to just focus on the cross valley orientation, it's not possible directly. But we did have supplementary lidars at the valley floor, and they were used to obtain the vertical profiles of the horizontal wind. And that gave us the sense of the along valley flows, wind direction and wind speed. But at least over the valley floor, we had some sense of that added three-dimensionality, or the sense of how the flow itself, to what extent the flow was perpendicular to our RHI transects.
Okay.
And yeah.
How many additional lidars were there then for the profiles?
So there were 3 additional lidars on the valley floor. 2 of them were doing the so-called VAD, or velocity azimuth display scan types. And there was another prototype instrument that was doing also a VAD type of a scan, but it was able to resolve the wind field in the lowest 100 meter. So inside the dead zone that the other lidars typically don't see inside.
Yeah, very useful.
Yeah.
And you show comparison between your ground-based lidars and airborne wind measurements. How do they compare, and what do you think? Do they complement each other? Are there pros, cons of both methods?
Right, so they complement each other in the sense that with the dual Doppler retrieval, we were able to get a very persistent and consistent sort of a mini climatology of the wind speed components across the valley and in the vertical. But that was essentially it. We don't have any information on the temperature, humidity, other scalars, or even the along valley component of the wind. And this is where having these aircraft measurements is really useful, because even though they are pretty expensive, that's one of their main cons. They're very expensive to organize. You have to wait a long time to reserve the aircraft to begin with. But it does provide these in situ measurements that can supplement the actual dual Doppler measurements, even though for a few isolated cases, which is what we did when we compared these in my recorded talk. Yeah. One of the main pros of the aircraft, it's these added benefits. But one of the main pros, I would say, of the dual Doppler setup is the fact that we can get these measurements, even though it's fixed in space, but we can get a very long-term, consistent data set. There's always a trade-off of having either spatially rich measurements or more temporally rich measurements.
It adds another dimension, yes. Right. Philip, did you have a question?
So in these aircraft data that you analyzed, how much along valley variability do you see? Is it comparable to the across valley variability that you observed, or is it more or less?
So when we look at the whole aircraft flight pattern, so we had multiple legs below the ridgeline, and they took, at least for a few cases which we focused on, they spanned about 15 minutes of aircraft time. And if we look at the collocated 15-minute period from the dual Doppler retrieval, we can actually see that the differences are actually quite minimal in both the stationarity of the flow and also the variability of wind direction, not just above the valley floor, but also going towards the sidewalls.
And similar question as I had asked Bianca already. Did you see a benefit of having 3 lidars instead of just 2? And did you try maybe to analyze only the cross sections of 2 and then saw the difference with the third one?
Right. So the main benefit of having 3 of them involved rather than just 2 is because we get most importantly, we get a larger aerial coverage. But Secondly, it's also useful because if one of them is offline, either not working or something is happening, there is also this matter of redundancy where we can still use the other two to get at least some information, which would not have been possible if we only had a setup of 2 lidars.
Yes, very good. And can you confirm that you have reached a 50 by 50 meter grid resolution on this plane?
Right. So as Bianca said, the size of the grid cell in this mesh is a function of the range gate resolution and also the angular resolution. Because we had very broad scans that were in some cases even a half circle, so between 0 and 180 degree RHI. And we wanted all of these scans to be synchronized, so they all lasted 1 minute, which means that they had to sweep that whole region quite quickly. And this already put a certain limit on how fine our mesh can be, because 50 meters is right on the border of having enough data, enough radial velocity estimates for each grid point to estimate the dual Doppler wind field. And we did some sensitivity study before the campaign to see how fine we can really go. And I think we did a 25 meter resolution. And in that case, you could actually see that there were sporadic grid points with no data, because the RHI field was so thinned out and there were actually grid points with no radial velocity estimates available. So this goes back to Philip's question, because if you want to estimate the turbulence, you have to have a much narrower scan that focuses on a much smaller spatial area, but these scans can be more temporally frequent. And in that case, you would have the opportunity to also have a finer grid mesh resolution to actually resolve the turbulence in a spatial manner, in a spatial manner as well.
Mm-hmm. Okay, thank you, Nevio. Then let's move on to Philip. You showed us a very nice presentation on the aircraft measurements, Doppler wind lidars pointing downwards, again in complex terrain. What is the accuracy of these aircraft measurements?
So that's a very nice question, but also very difficult to answer, because it's quite complex to measure with an aircraft. And when you put a Doppler lidar on the aircraft, then what you mostly measure is the aircraft speed. And that is typically 1 order of magnitude larger than the wind speed you're actually interested in. So you need to know it very, very precisely. And I did this in my work. It's not published yet, but there's many other effects you also have to consider. You do have one advantage though when you're on an aircraft, because the lidar does not only measure the atmospheric velocity, it also measures the ground return velocity. So it also measures the ground as a stationary target, and there you know the perfect result, which you should obtain after a perfect motion correction. The ground should come to 0 meters per second. So you can actually use that and reintroduce it into this motion correction process, for example. And with this, you can achieve quite high accuracy in these aircraft measurements then. So it's difficult to give you one number, but for a calm flight state, then I would say you can achieve a better accuracy than 0.1 meter per second with such an airborne Doppler lidar. But it depends on the flight state, it depends on many factors. But that's one estimate for the nadir viewing, just simply looking at the vertical wind. And if you want to retrieve the horizontal wind in these turns, like a VAD scan on the ground, then other effects like turbulence also have to be considered. So there again, it becomes a bit more complicated. But also there, the accuracy in the end is quite usable for measurements, I would say. So better than 0.5 meter per second accuracy in these measurements.
That sounds very good. What are the temporal and vertical and horizontal resolution of your LiDAR measurements?
Yeah, so the temporal resolution that we used for the LiDAR was a sampling frequency of 10 Hertz. So that's quite high. And then it depends on the aircraft speed. And there's the real advantage of the new system I showed in the presentation, because it's based on a very slow flying aircraft that flies at 65 meters per second. And then at 10 Hertz, you get a measurement for nadir viewing of the vertical wind every 6 meters, every 6.5 meters, which is quite a high resolution in a long track direction. The vertical resolution depends on the range gate length. So there, the system we used have a range gate length of 70 meters. So that gives one value every 70 meters in the vertical.
Hmm.
And yeah, it's wind profiling. It also depends on the scanning geometry that you use, or the like for a ground-based system. So
Yes.
they're approximately 1 kilometer you can achieve with such a system of a long track resolution for wind profiling.
Yeah, good. And yeah, you looked mostly at the boundary layer winds, vertical winds, and there were some strong variations you saw there. And related to that, how do you see the future of Doppler lidars, maybe not only airborne but also ground-based, in numerical weather prediction models?
Yeah, so I think these spatial differences are quite strong and can be measured with the Doppler lidar in a very unique way. And I think it's, first of all, of course, very interesting to compare these measurements to numerical weather prediction models and see if they can simulate anything like we observe in these complex terrains, any spatial structure that's similar, if they can really capture the spatial variability well for individual simulations. But of course, it's also interesting, I think, and especially also for ground-based systems, to take the LiDAR data and maybe assimilate it in a model. That would be another step, which I'm personally interested in, because it really gives you this vertically resolved information on the wind, which is hard to obtain using other measurements. So I think there might be an interesting opportunity to improve numerical weather prediction.
Exactly. Is there somebody working on it at KIT?
Not so far, no. I don't know anybody. Maybe do you know somebody who's working on this?
Not really on the coupling with validating the model output with aircraft data. It's mostly validating with ground-based LiDAR output.
Mm-hmm.
So,
And assimilation of Doppler LiDAR data?
yeah, that's what I was referring to, that there's no one working on the assimilation. I want to do some model comparison studies also for these airborne Doppler LiDAR observations. But the assimilation is another step, and I'm not sure if anybody's working on it. At KIT, there's no one working at it as far as I know, but maybe somewhere else I haven't heard of.
Yeah, it's an emerging field. It's not very well explored yet, so it's an opportunity as well. Okay.
I also
do you
have a question
questions?
for
Yes.
Philip. Yes, sorry.
Go ahead.
So Philip, besides the wind fields, did you also look at the like other parameters, like for example spectral width in your data, or like as indication for turbulence?
No. So what's obviously and easy to look at is the signal to noise ratio. I looked at that, and it reveals some nice layers in these boundary layers. But spectral width I haven't looked at, but turbulence quantities you can calculate. So because of this higher long track resolution, my work actually shows that you can not only obtain the mean vertical wind with high accuracy, but actually also calculate turbulent quantities, correcting for the pulse volume averaging of the LiDAR and some other effects. And my work really shows that you can obtain quite a high accuracy on these variance measurements, so to really obtain useful variance from the Doppler LiDAR.
So, but you're saying like you calculate the variances, like applying spatial averages to your data?
Yes.
Or how do you?
Yeah. Well, you have to average over a flight lag and then take the deviations. But then because of the LiDAR, it has this pulse volume averaging effect which you need to correct. But this is actually possible for such an airborne system to correct it.
Okay, yeah, so what I was referring to is like when you have the spectra stored, you could also look at like the intra-volume variability.
Yeah.
Like, but just looking at the spectral width.
Yeah.
And there you would not need to average so you would get a higher, a very high spatial resolution then.
Yeah, that might be interesting to do actually. Yeah.
I guess you stored the spectra during your measurements, yeah.
Very important. Always keep the spectra.
Yeah, but it's always a question if you have enough disk space.
Exactly, where to put it.
Yeah, but the flights are not that long, so that's not a big problem.
Good. Okay, thank you everyone. We would like to thank again our speakers for their time and their contributions to this webinar today. And we would like to thank the audience for their attention. We hope that you enjoyed our webinar. If you would like more information on our WindCube Scan product, we invite you to visit the Vaisala website. we're looking forward to hearing from you. Thank you.